In this video, we're going to take a look at a statically indeterminate problem involving our equations for axial loading. So, to start out with, let's define what a statically indeterminate structure is. We know that if we can solve a equilibrium problem with statics, if we have the same number of reaction forces as we have equilibrium equations, or to be more specific, non-trivial equilibrium equations. But if we have too many unknowns, then our structure is statically indeterminate. And so what we need in addition to those equilibrium equations are a compatibility equation, well actually one or more compatibility equation depending on how many extra reaction forces we have. And those along with the equilibrium equations are used to solve the problem. Compatibility, you can think of it as you need the displacements to be compatible with the problem geometry. And so we'll see that in this simple example here. So in this thing we've got an axial loaded member with 1,000 pounds being applied 12 inches away from end A. Both ends are fixed here. So if I draw a free body diagram of this structure, I'll replace the supports at A and C with reaction forces. And the only equilibrium equation, the only non-trivial equilibrium equation, because the sum of the moments won't give us anything because all the forces are along the same line. Some of the forces in the y won't do anything because we really have no forces in the y direction. So only the sum of the forces in the x direction is a non-trivial equilibrium equation, but it involves both the unknowns, Ra and Rc. So to be able to solve this, we have to add a compatibility condition. And the compatibility is relatively straightforward here. What's the deformation of the axial loaded member have to be? Well, because it's fixed on both ends, the overall length change is equal to 0, which means that the length change of the left segment plus the length change of the right segment has to be equal to 0. And our equation for the change in length of a segment is PL over AE. And in this case, we're assuming that the material is constant throughout and the same cross-sectional area on both segments, so we can get rid of AE out of both terms there. And so we have PL plus PL is equal to 0. Now, those stress resultants P's, we have to want to relate those to the reaction forces Ra and Rb. So let's start out by making a cut somewhere between A and B. And so the stress resultant in the axial direction, PAB in this case, has to be equal to the reaction force on the left end. And so if the reaction forces are in the direction that we've drawn them, which we assume they will be, then what that says is that segment AB is going to be in tension, which again makes sense because the 1,000 pounds that's pulling to the right is going to pull on segment AB but compress segment BC. And so we see that if we make a cut between B and C and look at the equilibrium of that cut segment, then the axial force BC, which I always draw that as though it were tension and let the sign kind of take care of itself. Well, in this case, PBC is going to be Ra minus 1,000. So if we expect the reaction forces to share that 1,000 pounds, so Ra is going to be less than 1,000. So PBC is going to be in compression. But again, that makes sense. If we put the 1,000 pound force in the middle, constrain both ends, we're going to be putting AB in tension, BC in compression. AC then is going to get longer, BC is going to get shorter, but the overall length change has to be equal to 0. So taking what we had earlier from the compatibility equation and now replacing the stress resultants PAB and PBC with the equations for the reaction forces that we came up with. And we can do a little algebra and solve for R of A. And so the reaction force at A is equal to 600 pounds. Going back to equilibrium, we know that two reaction forces have to add up to 1,000 pounds, and so that makes Rc 400 pounds. And so that seems to make sense because the load is applied closer to A than it is to C. You'll see the reaction force being more at A than at C. Alright, let's change that around a little bit. We'll keep the lengths the same. But now we'll make AB and BC out of different materials. So AB is going to be aluminum, and we'll give it a cross-sectional area of 2 square inches. And we'll make BC steel, so 3 times stiffer as far as modulus of elasticity goes, and also bigger in area with 4 square inches. So a lot of things are exactly the same. Our equilibrium equation is the same. When we did our cuts, free body diagrams of AB and BC, the relationships of the stress resultant reaction forces don't change at all either. So our compatibility equation, before we canceled out AE, but now that those values are different between AB and BC, we'll have to keep those in. And so we can write those as ratios. The lengths, the areas, and the modulus of elasticity, those ratios will define the ratio between PAB and PBC. You can see the negative sign here as well because we know that one of them is going to be in tension and one of them will be in compression. So plugging in the actual numbers here, we find that PAB is minus 1/4 of PBC. And again, the relationships between the stress resultants and the reaction forces are as they were before, and so that we can substitute those into the compatibility equation and solve once again for the reaction force at end A, and that ends up being 200 pounds. And from equilibrium then, the reaction at C is going to be 800 pounds. So because of the fact that we made AB much less stiff, both in modulus and in area, in fact we call the product EA, can be considered the axial stiffness, since it involves both the material property and the geometry property, the cross section. We've made BC a lot stiffer, and so it carries more of the load, and 800 pounds is now reacted at C and only 200 pounds at A. So what we learned from that was that we needed to use both equilibrium and compatibility equations to solve for a statically indeterminate problem. And in the second part of that, what we saw was that when we change the member stiffnesses in a statically indeterminate problem, that will change how the reaction forces are distributed. So that wasn't the case in a statically determinate problem. It really doesn't matter what the stiffnesses were, but anytime it's a statically indeterminate problems, because you're involving displacements as well, then changing the stiffness of the members will change the reaction forces.